Hello, my name is Owen Moore, and for my project for this class, I will be talking about limits. So what is a limit? A limit tells us what a value of a function is doing as it tends to a certain point. You can see over on this graph that as the x values tend to infinity, as they keep going towards the right, the values of f of x or y also approach infinity. Sorry about that. The values of f of x also approach infinity. This is a relatively informal idea of a limit. It's been used since about the time of the Greeks, although around the 1600s, while trying to find the slope of a tangent line, Pierre de Fermat found that he needed to have a definite way of taking the value of a limit. I mean, it was the start of calculus, so they needed to have a rigorous, mathematically sound way of doing this sort of thing, rather than just looking at it and say, oh yeah, the limit of this as x approaches 2 equals 2, or equals 4, sorry. So, a limit defined. This brings us closer to the formal definition of the unit. Sir Isaac Newton worked overtime. Not that he worked overtime, but over time he worked to bring us closer to the modern Epsilon-Delta definition of a limit. Which is a more formal definition based around the Greek letters epsilon and delta, which is that the limit as x approaches c of f of x equals L, which means that, and this is the important part, for every epsilon greater than 0, there exists a delta greater than 0, such that if x is an element of c minus delta and c union with c and c plus delta, that f of x is an element of L, or the limit minus epsilon and L plus epsilon. So what does that mean? Because that's a lot of words. Well, here we have a function, which is this red line, and we're defining a value of c in this function. And we want to know what the limit as x approaches this value of c is. Now, in this particular function, f of c is defined, and that would just give us the limit there. But to visually show you how the limit process works, let's go through it. We can draw lines and figure out, I mentioned this. We can draw lines and figure out that f of c, or L, the limit, is about there on the graph, but we really don't know anything else about f of c. To fix this, let's define a delta, which is a range of values on the x-axis. It can be as close to c as you want it to be, so let's just say there. So this will be our range of values, and now these delta values give us a range of epsilons on the y-axis that can help us pinpoint down where the limit is, because remember in our equation we said that for every epsilon greater than 0, which is just this distance, there exists a delta greater than 0. We already have these parts of the equation. Now all we need to do is prove that these last two parts. So we just need to pick an x value that's within our range of delta that doesn't equal c. So let's say this one, which is about 1.5. This is within our range. It's within the range of the delta, and as we can prove by just drawing lines through the equation, we can prove that it has an f of x, which is between this value, L, the limit, and it's within the end of the epsilon value, which we can prove that it's inside this range, at least graphically. So that's generally how this limit process works. It gets us, ideally you'll have a delta value that's a lot closer to 2, but just for the visual reference, it's nice to have them a lot bigger, but you want them closer to 2 so that you can have a better idea of what the limit is going to be. So, limits, like all things, have limits. A limit can't exist if the x value has 2 different y values being approached. This is because it's not a continuous function. You could say that the limit as x approaches 1 from the left on this function here is 1, and as it approaches from the right to 1 here is 2. But you cannot give it one limit because they're 2 different functions. They connect to 2 different points. As for this one down here, you could say that as x approaches 0 from the left is negative infinity, and as it approaches 0 from the right is positive infinity. But those they don't go to the same number, so it doesn't work as a function. How are limits useful aside from making cool graphs? Well, limits are the basis of derivative calculus. As mentioned earlier, they were required in the process of finding tangent line slopes, which is why Sir Isaac Newton, father of calculus, did so much work with them, because he was really into calculus. So let's do an example of a limit proof. Let's say, for example, we have this function. As the limit of x approaches 2 of x squared minus 4 over x minus 2. We need to prove that the limit of that is 4. Now, it's worth noting that 2 in this function is undefined. If we try to plug in 2 into the x here, it blows up. It doesn't work because we get a 0 in the denominator. And if you have a 0 in the denominator, there's a hole here. But we're trying to find the limit as x approaches 2, so we have to use the limit process to find this. So let's look at our definition we had. That for every epsilon greater than 0, there exists a delta greater than 0, such that if x is an element of this range of delta, but can't equal c, then f of x is an element of the range of epsilon. Note that it can equal L here. And I wrote down here, I didn't write up here, that this is less than epsilon. Yeah, this is just, it's just stating what we had up here, but in a more algebraic friendly version, which we're going to use to prove this. So we can fill in a couple values. We can fill in that c is equal to 2, which is this, it's commonly written as the limit as x approaches c, and we've filled in c as being 2. So we can put it down here in our equation. L, or the limit, equals 4. We're trying to prove that the limit equals 4. So we can plug that into our equation too. And we already know f of x too, which is this value. It's the function that we're trying to prove the limit of. So x squared minus 4 over x minus 2. We can plug that into here. So we get, if 0 is less than the absolute value of x minus 2, which is less than delta, then the absolute value of f of x minus L, or the whole quantity of x squared minus 4 over x minus 2 minus L, which is 4. And that has to be less than epsilon. So we could, it makes sense to simplify this starting with this, because we already have basically every value for it. So as we do this, we can split apart this x squared minus 4, and we get x plus 2 times x minus 2 over x minus 2 all minus 4. Then we can sort of we can simplify this to take out this x minus 2, which leaves us with simply, like, we can actually do this division problem. We can say that because of that, x plus 2 minus 4 is our true equation. And then we can combine these like values to get x minus 2. The absolute value of x minus 2 is less than epsilon. Now, the absolute value of x minus 2 less than epsilon is coincidentally close to the absolute value of x minus 2 is less than delta. So we can say from this that delta is equal to epsilon, which means that for every epsilon greater than 0 given to us will work, because we will always have a delta value that is greater than 0. And we know this because they're literally the same value, and you can't give us a value that doesn't fit these requirements. So we can prove that way that it all equals 0. And here's a little graphical representation I made. Any value on this epsilon here that's given to us will be within these delta values, because it's 1-to-1 aside from this little the hole in the graph here. So we can get as close as we want to this, and it will still give us a delta that is greater than 0 and does not equal this 2 value. So that is my example of a limit, and that was my presentation on limits. Thank you.